Hello everyone, myself Heming Sathwara. Today we are going to discuss about diode approximation. So today outcomes are first approximation, then we will see about second approximation, then next is third approximation. So let's start with PN junction diode. So as we discussed in our first lecture, PN junction diode is two-terminal device which is semiconductor device. That two terminals are, one is anode, second one is cathode. Anode is positive and cathode is negative. So current always flowing from anode to cathode, means positive to negative. So this is the construction of PN junction diode and the symbol of PN junction diode. So basically PN junction diode made from two different types of material, one silicon and second one is germanium. So let us discuss about approximation. What is diode approximation? So diode approximation means it is mathematical method used to approximate the nonlinear behavior of diodes to enable the calculations and circuit analysis. Or we can say diodes which is present in this circuit, how gets analyzed, means this is the diode approximation. Based on this approximation there are different types of parts: first approximation, second approximation and third approximation. So let's start with first approximation. So here we can see this is the first approximation. First approximation is basically known as ideal diode. So here we can see the different types of cases, case number 1 and case number 2 along with the graph. So in this approximation, diode assumed as an ideal diode, and generally this analysis is used for theoretical purpose, but practically it is not possible. So here we can see in first approximation diode acts a perfect switch. So there are two different types of cases. We can see case number 1, forward bias, which means closed switch. Number 2, reverse bias, which is basically reverse open switch. So here take first case number 1, it is forward bias. Forward bias means current always flowing from anode to cathode. So basically we can say current flowing from plus to minus with the direction of symbol. So it means it is equivalent to the closed loop. So here we can see this is the equivalent circuit of forward bias, closed switch, and closed switch means current always flowing from one end to another end. So we can see it in the graph, the current is flowing, but we cannot measure voltage across this wire. So this is the zero voltage, zero forward voltage VF, and second one is reverse bias. In reverse bias there will be a open switch. Open switch means no current flow from this circuit. So here we can see this is the graph of reverse bias. So it means zero reverse voltage, which is known as IR. So this is the first diode approximation in which we consider only diode as a switch. Then second diode approximation, here we can see in second diode approximation is considered as a forward bias diode in series with a battery to turn on the device. If we consider here silicon material, then the diode needs to turn on at 0.7 voltage. If we consider here germanium material, so diode needs 0.3 voltage. So here we can see the diode turns off if the voltage is less than 0.7 for silicon material. So here we can see different types of cases. Case number 1 for forward bias and case number 2 for reverse bias along with graph. So let's take with case number 1, forward bias. So current always flowing from plus to minus. Here the equivalent circuit of forward bias is equal to closed switch along with the battery. So as we discussed in starting of second diode approximation, battery is needed in this circuit diode. So here the graph is at VB. VB means it is the biasing voltage. So if silicon material is used, that means 0.7 voltage. So this is the graph of the forward bias. Now case number 2, reverse bias. In reverse bias, as we discussed, the circuit becomes open. Why? Because diode only works in forward bias, not in reverse bias. So your direction is 0. Here we can see this is the 0 graph. Now let us discuss about third diode approximation. So this is the advanced analysis, then the second diode approximation. In this diode approximation, we include voltage across the diode and along with bulk resistance, which is known as RB. In bulk resistance, we can consider RP and Rn. Now, what is RP and Rn? RP is the p-type regions resistance and Rn is the n-type regions resistance. So combination of this RP and Rn becomes RB, which is known as bulk resistance. Bulk resistance is very low, such as greater than 1 ohm or less than 10 ohm. So the sum of this ohmic resistance becomes bulk resistance, and its equation will be RB is equal to RP plus Rn. So here this is the bulk resistance along with battery. So in this case number 1, forward bias. So always current flowing from plus to minus means anode to cathode. So it becomes closed switch, but here we add one battery and bulk resistance RB. So its graph is little bit different than the first diode approximation and second diode approximation. Like we can see, this is the closed switch, current flowing from plus to minus this direction. So your graph will be like this. It on at 0.7 voltage if there is a silicon material. If there is a germanium material, so it on at 0.3 voltage. So here we can see this is the VB. It is biasing voltage. Here your graph will be starting like this in linear manner. Why it is linear? Because here we are added RB, which is known as bulk resistance. Basically R is equal to V by I. So due to this reason, here we can see this type of graph. Now let us discuss about case number 2. Case number 2 is reverse bias. Similarly, as we discussed in first diode approximation and second diode approximation, here also your circuit will be open because in diode it is not working in reverse bias. So always current flowing from anode to cathode, that means closed switch. If current flowing from cathode to anode, then it will be open switch like this. So its graph obviously straight line because no current flow from this circuit. So this is the third diode approximation. Now let us discuss about its application, where we can use this approximation. So we can connect it to the real-time example. Like someone say, how old are you? You may say, I am 21 years old. That is not more information about your age. So it becomes ideal diode. It considered with the ideal diode. You might say, I am 21 completed and 22 is going on. So it is little bit more information than the first one. So it becomes more accuracy and practical purpose. So it considered as a second diode approximation. If you want to be more accurate, then you might say, I am 21 years, 9 months and 3 days. So it is exact calculation with accurate analysis at laboratory level. So it considered as a third diode approximation. So with this example, we can understand Why here we are using approximation with the diode? Basically, first diode approximation is basic level, which means ideal one. We cannot get perfect information about the diode or circuit. Second diode approximation give you some more information than the first approximation, like initial voltage, cutoff voltage we can say. It is 0.7 voltage. And if you want exact calculation with accurate analysis at laboratory level, then you have to use third diode approximation. So this is the application of the diode approximation. Here we can see few quiz are available for this, for understand this topic thoroughly. So we can see number one, in first diode approximation of diode, the diode is known as, it is ideal diode. Number two, if diode is connected in forward bias, then it behaves as, so two options are there, closed or open. So if diode is connected in forward bias, so it behaves as closed switch. Similarly, number three, if diode is connected in reverse bias, then it behaves as open switch, as we discussed in our theory. So these are the few questions for self assignment. You can do it. So that's all for today's lecture.